Watch what you say now because it's being recorded. As you know, the internet never forgets anything. Let's see, is that buzzing sound coming from me?
Oh, sorry. No, it's me. I have I was unmuted. Sorry.
Okay, good. Mute that. Good. Thank you very much. Now, let me get this enlarged here. We finished last time in the middle of a derivation, so it's going to take a minute or two to bring us up to speed as to where we were. So let me start with that now. We have here, excuse me, did somebody say something? Okay. We have here at the top the Schrodinger equation. Well, we're going to work in natural units where h bar equals c equals 1. So the h bar that appears in the Schrodinger equation, I really ought to take it out there and there, that goes. But otherwise, this is an old Schrodinger equation, and this is a prime version of it. The relation between the old and the new wave functions is given by an operator e to the s, where s is anti-Hermitian, meaning that e to the s, the operator is unitary. Then by plugging this transformation of the wave function into the original Schrodinger equation, we obtain the new Hamiltonian as expressed down here. There is one term which is the old Hamiltonian conjugated by the unitary operator. And then there's another term that comes from the time dependence of the unitary transformation, which you see here. These two terms were expanded in power series of iterated commutators with S. We call S, by the way, the generator of the unitary transformation. But both these terms can be expressed as power series of iterated commutators involving S. And we use the abbreviation here, L sub S with an operator X. It means the same thing as a commutator. So L sub S cubed means the 3 times iterated commutator S with S with S with X, like that. That's how it goes. In any case, if we apply this to H, the first term here, we get a series that looks like this. This is the exponential series of the L sub S, or iterated commutators expanded out. For the time-dependent term, we get another series, which is down there. And these two series were derived in the first homework problem of last semester. Now this is the basis of a version of perturbation theory, which we're going to apply to our problem. Our problem is a Dirac equation involving a Dirac particle with a G factor of 2 interacting with an external electromagnetic field. We write the Hamiltonian as the sum of 3 terms. The first one is m beta. That's otherwise mc squared beta. That's the dominant term in powers of what we call eta. Eta is basically the ordering of the terms in powers of v over c, which we regard as being small because we're interested in a non-relativistic limit. In any case, that's the leading term. The first order correction I call O, and the second order one I call E, which stands for odd and even. The odd term more explicitly is alpha dotted into pi, where pi is the usual kinetic momentum. It's p minus q times a, where a is the vector. That's supposed to be an a there. That's the vector potential. And the q phi is, of course, the electrostatic potential. These are called odd and even because they're based on the Dirac matrices. The alpha matrix is odd in the sense that it has off-diagonal elements, but it's 0 in the diagonal. And the beta matrix is even because it's got 1s and minus 1s in the diagonal and 0s in the off-diagonal. In other words, the even matrices are block diagonal and the odd ones have off-diagonal elements. This final term E here, which is equal to Q phi, is even because it's effectively multiplied by the identity matrix 1, which of course is an even matrix having just 1s on the diagonal. This is a 4x4 identity, and we could write it as in terms of 2x2 identities. So that's the problem. That's the Hamiltonian we're going to deal with, and its ordering in this order parameter eta. Now then, let me tear this off so I can move it up some. So now if we apply this power series here of iterated commutators to the 3 terms, m, beta, O, and E, of this Hamiltonian H, that's going to take care of this first factor here, conjugating H. For the m beta term, what you get if you just write them all out, I've just carried out the exponential series out to 4th order. You see, this is 3 factorial, 4 factorial, ls to the 4th acting on m beta. It's just this m beta thing with the iterated power, with the exponential power series of iterated commutators. That takes care of the transformation of the m beta term. The O term is similar, except it's shifted in ordering. The first order is O, and then we get LSO and LS squared O, LS cubed, and so on, 2 factorial, 3 factorial, etc. And likewise, the E term appears here starting at 2nd order, 3rd order, and 4th order, again, iterated commutators. And then there's the terms that involve S dot, which come from the time-dependent term up here, which I won't write out explicitly, but if you wanted to, it would look like this. It'd involve iterated commutators of S dot. All right. Now then, the strategy that we follow here. So this collection of terms that have all been added up here, quite a few of them, is what we get if we just transformed H into H prime using an arbitrary generator S. But the strategy we're going to follow is to choose the generator S so that the order A to the first power terms vanish. These are the ones that have off-diagonal elements in the Dirac matrix, as to say they're odd, like the alpha, you see, that's what it is. That's, oh, it contains an odd term, contains alpha. So we choose S to make this term vanish, and that kills the first order correction and the first order term in the Hamiltonian, and moreover makes what's left over, at least at zeroth order and second order, is now even, i.e. diagonal. So we want to choose S, as I say, so that LS acting on M beta is equal to minus O. It turns out the S that does that is 1 over twice the mass times the beta matrix times O. And this you can see is of order eta to the first power here, because O itself is of the first is to the first power in eta. By the way, the reason that's first power in eta is because it contains a kinetic momentum, which is mv, and the velocity v is of order eta. That's why the potential energy goes like mv squared. It's the same order of magnitude as 1/2 mv squared, and so that's a second order in eta. That's the reason for the ordering here in powers of v over c. But in any case, the generator's first order in powers of v over c. And that's why when I carry out these iterated commutators here, I increase the order of eta by 1 at each step, as you can see. So the LS to the first power is eta to the first, LS squared is eta squared, and so on down the line. So I've aligned these columns of these terms so that the different orders here are shown, second order, third order, fourth order, and so on, are shown in vertical columns. All right. By the way, so the S then is of order eta to the first power. By the way, a useful commutator, a useful anti-commutator in this calculation is the anti-commutator of beta with O. Well, O is the same thing as alpha dotted into pi, and pi is the kinetic momentum. So in dealing with anti-commutators like this, we're going to have to do some calculations tonight involving especially commutators, but anti-commutators also. You can see the whole work of the perturbation series is doing iterated commutators. That's what's involved here. In any case, this is an anti-commutator which arises, and the way to evaluate it is to first of all notice that the Dirac matrices beta and alpha, which appear here, all the Dirac matrices really, they're all of order unity because they just got numbers in them which are of order unity. Pi, on the other hand, is a spatial operator, purely spatial operator, which therefore commutes with all purely spin operators, which are the Dirac matrices. So that's a useful anti-commutator. Now, I think the first thing I want to do is to actually show you that this generator chosen in this way. I didn't derive this, I'm just quoting it, but I will at least go to the effort of showing you that it does satisfy LS acting on M beta, gives you minus O, and thereby causes these red terms, circle terms, to vanish, to go away, which is the whole strategy of this transformation, at least at first order. So allow me then to move on to actually doing that. Let's start by showing that that LS M beta is equal to minus O. So LS M beta, and S, I'll remind you, is 1 over 2m times beta times O, and O, I'll remind you, is equal to alpha dotted into pi, which is the kinetic momentum. So LS M beta's got a factor of, well, this is the commutator of S with M beta, that's what it means. And the S has got a factor of 1 over 2m, and the M beta's got a factor of m, which are constant, so I'll take that out. So what's left is a commutator of beta times O with beta. And so that's equal to 1 over 2m times m is 1/2. And then the commutator then is beta O beta minus beta times beta O, like so. Well, beta squared is equal to 1. And beta and O anti-commute. So if I swap the order of them, that's this anti-commutator I showed in the last page. So if I swap them, I get a minus sign, and it gives me another, now with a minus sign, beta squared O, but beta squared is 1, so this just becomes minus O. So both these terms are equal to minus O, and cancels the 2, and we just end up with minus O. And that's what we wanted to show. We wanted to show that LSM beta was minus O, so these red terms disappear. And that was the justification for choosing this. One can also show that this, explicitly show that this S is anti-Hermitian. It's easy to do because both beta and O are Hermitian, but they anti-commute with each other. So if you swap the order, you get a minus sign. All right, in any case, so e to the s is therefore is unitary. All right, having done that then, we can observe some things. Let's go back to our series here. Let me draw your attention to the first two rows of this series. We've got ls to some power and m beta on the first row, and then we've got ls to some power and o on the second row. Let's look at these two here. We've got on the order eta squared terms. We need to evaluate lso plus 1/2 ls squared m beta. Well, it works like this. Let me write it down. We've got LSO plus 1/2 LS squared M beta. But LSM beta, as I just showed here, is equal to minus O over here. So this is LSO for the first term, and the second term is minus 1/2 LSO. And so the result is just 1/2 LSO. And so go back to this equation, and these two terms combine together to give you 1/2 LSO. If you do something similar in the cubic terms, you're basically just subtracting 1/2 minus 1/6, which gives you a third, and the answer is 1/3 LS squared O. And as far as the fourth order term, you subtract 1/6 minus 1/24, and that gives you 1/8. And so the answer is 1/8 LS cubed O. And so what I'm going to do is write down H prime again, but clean up these first two rows, and then this third row, I'm just going to copy. We'll worry about this S dot terms in a minute. So if we do this, then here's what we get for H prime. We get H prime is equal to M beta. Let me draw a line up here to separate this off. We get M beta, which is order eta to the 0. Now we killed the terms at first order in eta, so I have a column I can skip now. But the next order is order eta squared. And that's going to be 1/2 plus 1/2 LSO. And then in order eta cubed, we're going to have plus 1/3 LS squared O. And then in order eta to the fourth, we're going to have plus 1/8 of LS to the LS cubed O, like this, dot, dot, dot. For the even terms, I just copy them from the previous line. It's E plus LSE plus 1/2 LS squared E. By the way, the L here in the LS is just short for Lie because commutators are like Lie algebras. That's really what it means. It means to form the commutator with S with E. Now, what about the dot terms? Let's look at them. S dot would be equal to the derivative with respect to t of 1/2m times beta times O, but O is the same thing as alpha dotted into pi, and pi is the same thing as p minus qa, like this. And the only thing in this expression which depends on time is the vector potential A. And so this becomes 1/2m beta times alpha with a q here comes out, a q factor comes, charge q with a minus sign comes out, alpha dotted into partial of A with respect to t. Now, in the last lecture, I explained to you the ordering of various terms, various expressions that occur in this problem based on a reference system, which was the ground state of hydrogen. In that case, we found that QA was of order eta cubed. This is assuming that magnetic fields are internally generated inside the atom, such as, for example, by the orbital motion of the electron. Or in the case of spin orbit effects, you may recall, we talked about the orbital motion of the proton as seen in the electron rest frame. That's another example of a magnetic field of the order, but I mean an internally generated magnetic field. Anyway, for such magnetic fields, the vector potential goes like, is of order eta cubed. And so you can see then that, and then that implies, on the other hand, the ddt is of order eta squared. So the q times dA dt, which by the way is otherwise the same thing as a transverse electric field, that's of order, in Coulomb gauge it is anyway, that's of order eta to the 5th power. And so this term here, this q here times this dA dt is of order, the whole thing turns into being of order eta to the 5th. And therefore it's off the charts here. And the same thing is true for all the other S dot terms that would in general appear due to that time dependence of the transformation. They don't actually appear at all if we're just going to go to 4th order. So this much is what we've got left over after we make that choice for the first generator S. All right. So this is the outline of the basic procedure so far. Are there any questions about it before I go on? It's an interesting procedure. It's an interesting version of perturbation theory. There are versions of classical perturbation theory that are based on iterated Poisson brackets, and this is kind of a quantum analog of some of that. And all that, in fact, all that bound state perturbation theory we did last semester can also be done by means of iterated unitary transformations based on the same general idea. It's actually older than it's an older version of perturbation theory, as a matter of fact. All right, so at this point, let's do the following. As you can see, we've block diagonalized the Hamiltonian through second order. We got rid of the first order terms, which were off diagonal. All of the odd terms are off diagonal. We didn't get rid of the eta cubed term because we only had one generator, and that was only able to get rid of one of the things, the second order term. So this still contains off diagonal elements. But if we truncate the expansion out at second order, which means order v over c squared compared to mc squared, then we've got a Hamiltonian that's been block diagonalized. So let's take a look at what that Hamiltonian is, just to see what we got so far before we go on to higher order. So the main thing that's not clear, I would say, is that, I mean, since m beta is clear and the E is clear, the E is the same thing as Q phi. The main thing that's not clear is this 1/2 LSO. Let's talk about that. In fact, while we're at it, let's talk about these other LSO things here. So let's look at LSO. This is the same thing as the commutator of S with O, like that. And S has got a factor of 1 over 2m, like so. And then otherwise it's beta times O, commutator with O, like that. And that's equal, as you can see, the calculations are straightforward. It's 1 over 2m beta O squared minus O times beta O. However, beta and O anti-commute, and so swapping them and changing signs just doubles the first term. So what we get is, let me write it down here, is we get LSO is equal to 1 over m times beta O squared, like that. And now it's just as easy to compute the higher order powers of LSO just by forming another commutator with with S. And if you do, you find that LS squared O is equal to minus 1 over m squared times O cubed. And you find that LS to the cubed O is equal to minus 1 over m cubed. I hope I'm saying this right, times O to the fourth, like so. This is what you get if you carry, this is a beta in here, excuse me, beta times O to the fourth over m cubed. This is what you get if you carry out these iterated commutators out to which really takes you out to the fourth order term. So allow me to rewrite this H prime now with these substitutions down here, and I'll show you what we get if we do that. Let me get the paper organized. So I'm what you see at the top of the page, I'm just going to rewrite it now using the substitutions. So we have H prime is equal to, at order eta to the 0 is m beta. At order eta squared, we have 1/2, we have plus 1 over 2m beta times O squared. At order eta cubed, we have a 3 here. We have minus 1 over 3m squared times O cubed. And in order eta to the fourth, here we have minus beta over 8m cubed times O to the fourth. And then the E series I'll copy, LSE plus 1/2 LS squared E. And so this is our Hamiltonian then, where the first line made more explicit. Now, let me introduce my cutoff at order eta squared again, as I did on the last page. And let's just look at what we have to the left of the red line, which is our main result, but only carried out the second order in V over C. So the only term whose meaning is not totally clear is this 1 over 2m beta O squared. Beta is pretty clear, it's just the beta matrix. What about O squared? Well, O squared is the same thing as alpha dotted into pi, quantity squared. And this is, we can write this out in index notation as alpha I pi I times alpha j pi j. I'll show you how you calculate this. The alpha is purely a spin operator and the pi is purely spatial, so they commute with each other. But the alpha I and alpha j don't commute, and the pi I and pi j don't commute either. So we have to respect the ordering of those factors. So this thing can be written as alpha I times alpha j times pi I times pi j. That's okay to rearrange it like that. Now the alpha matrix, Dirac matrix, has got Pauli matrices on the off diagonal, like so. And this makes it easy to compute alpha I times alpha j. Just write it out and multiply it using the algebra of the Pauli matrices. And if you do, you find it's given by delta ij plus I epsilon ijk times capital sigma sub k, where capital sigma is the Dirac matrices that have Pauli matrices on the diagonal and zeros in the off diagonal. So capital sigma is an even matrix, as you see, whereas alpha is odd. I'll remind you that capital sigma rose initially, at least in my lectures, about one or two lectures ago, as the generators of spatial rotations when it comes to those D matrices that transform the Dirac equation. Basically, they generate Pauli two-component spinor rotations on the diagonal and then zeros in the off diagonal. In any case, that was the original place where the sigma occurred. But this is a useful identity in this calculation, in this Foldy Wouthuysen work. And in particular, it means that this product up here, we can rewrite it this way as delta ij plus I epsilon ijk sigma sub k times a pi I pi j, like so. And as far as the delta ij goes, that just gives us a square of the vector pi. And then the plus I epsilon ijk sigma k pi I pi j, I'll just copy that for the time being, second term. In this second term, the I and j and the epsilon are antisymmetric. And that means that I can replace pi I pi j with the antisymmetric part of that, which is pi I pi j minus pi j pi I, but I have to divide by 2 to compensate for having 2 terms. So there's nothing wrong with doing that. However, by doing that, what you see appearing here is the commutator of the kinetic momentum pi I pi j. And we've done this commutator in problems with magnetic fields about 1,000,000 times so far in this course. And the answer is that this is equal to I times the charge Q times epsilon ij, let's call it ijl, times the magnetic field BL. The commutator of the pi's with the vector potentials generates the curl of A and gives you a magnetic field. I think we did this with velocity operators in the non-relativistic theory, but the calculation is really the same, except for a factor of mass. It's the same operator. It's P minus QA is what it is, essentially is what pi is. All right. Anyway, when we combine this together, you see one epsilon ijk here and an epsilon ijl there. There's an epsilon identity, which is given in one of the appendices to my notes. It's epsilon ijk times epsilon ijl is twice Kronecker delta KL. You get a factor of 2 because you got 2 indices you're summing over here. In any case, if you put this together, then what it ends up doing is giving you a contraction between sigma k and the BL to give you sigma dot B. The I times the I is minus 1. The 2 from here cancels a 2 there. And anyway, the result of this is that O squared now becomes equal to pi vector squared minus Q times capital sigma dotted into the magnetic field. Okay? And if I now go back to the Hamiltonian that we've got up here, this means the Hamiltonian through second order, what we call H prime, is equal to m beta. And then we have plus 1 over 2m times beta times, let me write this way, is beta times 1 over 2m pi squared, 2m pi squared, minus q over 2m times capital sigma dotted into the magnetic field. And then finally we have the q phi, which is the E up here, which hasn't changed. And so now, having done this, this is still a 4x4 Dirac Hamiltonian, a 4x4 matrix, spinor matrix, but it's been block diagonalized. It doesn't have any off diagonal elements. And so if we let the wave function psi prime have an upper and a lower 2-component spinor, call them phi and chi, you might put primes on them if you want to indicate that where they came from, then what you get is 2 decoupled 2-component spinor equations. And if we talk about the Hamiltonian just for the upper part, let's call it H upper. Let's see if I have room to write it here. If we talk about the effectively now a Pauli Hamiltonian just for the upper part, what is it? Well, the beta matrix in the upper part is just the identity. So I just get M for the first term. And for the second term, again, the beta matrix is 1 and it's the identity in the upper half. So then I get pi vector squared over 2m minus q over 2m sigma 2m q over 2m times the upper part of capital sigma is lowercase sigma, so it's lowercase sigma dotted into b. And then the q phi is multiplied by the identity, so the upper part of that is just q phi. And what you can see appearing here, although it's written in natural units, what you can see appearing here is the Pauli Hamiltonian for a spin a half particle, the g factor of 2. G factor of 2 is contained in this term. This is really the mu dot b. This is minus mu dot b here. It's appearing here with a g factor of 2. This, on the other hand, is a kinetic energy with a p minus a squared term in the numerator and the 2m in the denominator. Here's the potential energy, q phi. These last three terms are really the Pauli Hamiltonian. The m that appears here in front really means mc squared. This is a constant that is just added to the Hamiltonian. You can add any constant you want to any Hamiltonian you want, and all it does is just change the phase factors in the time evolution, but it doesn't change any physics at all. And so by just shifting the Hamiltonian by a constant, you recover the Pauli Hamiltonian with no loss in physics. Now, so in other words, by diagonalizing by this formal method, by diagonalizing the original Dirac equation through second order, we obtain the Pauli equation with a g factor of 2. This is the same result we got earlier by more ad hoc methods in evaluating the non-relativistic limit of the Dirac equation. You recall we eliminated the lower component with an approximation and plugged back into the upper component. Anyway, in fact, you should be more familiar with that because it was part of this week's homework to do the analogous calculation in the 2+1 dimensional case. But anyway, that was the idea. So we're deriving the same result. We don't really have anything new at this point, except that we've derived it by a new and more systematic method. However, what we have now is the option of going on and carrying this out to higher order in V over C, and that's what I want to do next. We'd like to go to V over C to the 4th power. In order to do that, we need to eliminate the terms at order eta cubed, the third order here in V over C cubed. These are odd terms. If you want to check them, you'll see that they're odd. They're all off diagonal, so we'd like to kill them. Well, how do we do this? Well, what we do is we use a second Foldy Wouthuysen transformation. We go from H prime to, let's call it H double prime. Let's write psi prime double prime is equal to e to the s prime times psi prime. So s prime is a new generator. And this gives us a new Hamiltonian H double prime is equal to e to the s prime times h prime times e to the minus s prime plus s prime dot terms, which will turn out to be negligible because they're even higher order than the s dot terms we had before. And so we just need to do this conjugation. Now what we want to do, and so you can write this out as h prime plus ls prime acting on h prime plus higher order terms like that. Now we want to choose the s prime to go back to what our h prime looks like, as I mentioned earlier, to kill the order eta cubed terms. And that means we're going to choose an s prime, which is order eta cubed. So let's write out the exponential series now for all these terms, 1, 2, 3, 4, 5, 6, 7 of h prime. Let's write them out to see what they look like after we carry out this unitary transformation. So here's what we're going to get then. The h double prime is equal to, well, there's the first term is m beta. Okay, let's do that one first. So we have m beta, and that's of order eta to the 0 power. We're going to have an eta to the 2nd power, an eta to the 3rd power, and an eta to the 4th power. Let's write them out like that. I need to leave space for them. Now the first correction term is going to be ls prime applied to m beta, but s prime is order eta cubed. So this ls prime m beta is actually out here, ls prime acting on m beta. That's a 3rd order term, and it doesn't contribute at 2nd order. And then the one that involves ls prime squared, that's going to be order eta to the 6th, so it's off the charts here because we're only going to eta to the 4th. So this correction term is all we need. Now to go back to our h prime, the next term is this 1 over 2m beta o squared. That's at order eta squared, so let me write that down. So I'll have plus 1 over 2m beta o squared here, all right? And then we need an ls prime acting on that, but ls prime, s prime is order eta cubed, and this is already order eta squared, so that gives you order eta to the 5th. And so the correction term for that's off the charts. Also, it's gone, it's over the chart, off the charts. Okay, let's move on to the next one. It's minus 1 3m over 3m squared times O cubed. And that's at third order. So I'll put it in here. -1/3m² O cubed. And again, the correction term is off the chart, said the order 8 to the 6. And then finally, we've got -1/8m³ times O to the 4th. And this should have a beta in here too. And then the first correction of that term is also off the charts. So that takes care of transforming the entire first line here. Likewise, in the second line, we just need to copy it because all the correction terms are off the charts. So we have E here, we have LSE here, and we have 1/2 LS² E here at fourth order, and then the rest of this is all off the charts. So let me separate this with lines so we can see what we've got here. Now our strategy is going to be to choose. You see, the only place where there's a correction term is right there. It's at this third order, LS prime M beta, right there. So what we want to do is to choose LS prime to make this entire cubic term vanish. And let me just say that you can do it. And I don't want to write down what S prime is because we don't actually need it. The point is that it's possible to find an S prime to make that happen. And basically the reason is because the terms we want to kill are purely off diagonal, and it's easy to show that you can do that with a commutator of S prime with M beta. And so there exists an S prime that causes these terms to cancel. And if we do, then the H double prime, which is the Hamiltonian after what we now have a second Foldy Wouthuysen transformation, consists of just 0th order, 2nd order, and 4th order. That is to say, it's block diagonalized through 4th order. And the upper and lower two component spinors are completely decoupled at those orders. All right, so this goes to 0. And as far as the rest of it goes, if we want to get H double prime, we just need to evaluate things. Well, we know what eta to the 0, order eta to the 0 is, and eta squared. We just talked about that. That was basically the Pauli terms. These and these 3 terms here give us that. The O squared generated 2 terms, including the mu dot B correction. So what we need to work on is to evaluate the 4th order terms, which there's 2 of them here. Let's look at them. Let's look at the first one. That's minus beta over 8m³ times O to the 4th. Now look at O to the 4th. O to the 4th is the same thing as alpha dotted into pi quantity to the 4th, because that's what O is. And let's see here. Or this is the same thing as alpha dotted into pi squared quantity squared, like so. Well, alpha dotted into pi squared, we just evaluated that, and that was the same thing as pi squared minus q times capital sigma dotted into the magnetic field. And that quantity is squared. Now pi squared is order eta squared because it's basically like a kinetic energy. It's a square of it's basically mass times m squared times v over c squared. V over c squared makes it order eta squared. What about q times b, the magnetic field? Well, we can go back, assuming the magnetic field is internally generated, we can go back to our table here, and q times b is of order eta to the 4th. We determined that in the last lecture. And I just bumped my just a minute here. I've got to rearrange this so it's oriented right. So so this correction term is order eta to the 4th, but we're only interested in this quantity order eta to the 4th anyway because it's a 4th order term. So we can neglect this sigma dot b term. It's not going to involve the correction at all. And what we get then is pi squared quantity squared. Okay, but now pi squared, this is the same thing as P minus QA quantity squared. Now you see, that's what that becomes. P is a momentum is of order eta because it's basically like MV, whereas the QA, it turns out, is order eta cubed. And again, if you just want to evaluate this to 4th order, which is all we do, then the Q eta squared can be neglected, and the whole thing just turns into the momentum P to the 4th power. And so carrying things out just to 4th order, this becomes, let me write it down here. The first term becomes minus beta over 8m³ times the momentum P to the 4th. Okay, let me box that because that's the boiling down of the first of the 2 terms that we have at fourth order, like so. All right, now, so Perhaps you can see appearing here in this term is actually the relativistic kinetic energy term that we talked about last semester. This is really a Dirac Hamiltonian, not a Pauli Hamiltonian, but the beta matrix has got 1 minus 1s in the diagonal. And if you just look at the upper part, you can see it's going to be minus p to the fourth over 8m cubed. And if you restore ordinary units, there's a factor of c squared in it. And that is precisely what we call HRKE last semester when we were doing fine structure. And so that fine structure term comes out of the Dirac equation in this manner. What about the other two terms? Or excuse me, what about the other term here, the 1/2 LS squared E? Let's work on that. Calculating this takes a little effort. It gives us some practice in actually calculating commutators. I'll do the calculation for you. Obviously, the strategy here is to first compute LS to E to the first power and then form another commutator, do it again. So let's do it that way. And I'll outline the calculation for you. And so let's look at LSE. That's equal to the commutator of 1/2m beta O, which is what S is, with E, which is Q phi, like this. And O is, of course, the same thing as alpha dotted into pi. All right. And what we have here is, in fact, let me write it this way. Let me write it more explicitly. This becomes this is 1/2m, by the way. It comes out as 1/2m times the commutator of beta times alpha dotted into pi, commutator with phi, and the q comes out also. Take the constants out, and it turns into this commutator. Now again, beta and alpha are spinor operators, and pi and phi are purely spatial, and they commute. This means the beta alpha can be taken out of this commutator. This can be written as q/2m. Let me write it this way: is beta alpha sub I times the commutator of pi sub I with the scalar potential phi, like so. Now this becomes a purely spatial commutator, and commutators with pi are the same as commutators with p because the vector potential commutes with a function of position. So this thing turns into, this is just a standard commutator of p with a function of x, basically. It turns into minus I times partial of phi with respect to xi. So you see it makes the gradient of the scalar potential, which is the electric field, or more exactly, it's the longitudinal part of the electric field. There's a minus sign, of course, as well. So minus d phi dxi is the longitudinal electric field. So let's write this as we have IQ over 2m times beta times alpha sub I. Alpha sub I is then dotted into the ith component of the electric field. I'll write it as alpha dotted into E, electric field like this. So this is LSE. Let me box that so I can draw my eyes. My eyes can find it easily if I'm looking for it later. That's this first commutator. All right. I'm writing this E as the total E, but if you look at the transverse contribution, it's of higher order and can be neglected. This is E is really the gradient of phi is dominant, and that's really all we need here for this alpha dotted into E. All right, but we now need to compute LS squared and times a half, so we need to form the commutator again. So let's show you how that works. It's a calculation to do it. It's the last calculation of this whole business. So let's compute LS squared E, which is going to be from the first LS, there's a factor of 1/2m, and then for the second one, there's a factor of times IQ over 2m, and then we have the commutator of beta O, which is beta alpha dotted into pi. That's from the S that's hiding in this LS here. And then what's left over for the LSE has got the alpha, it's got beta times alpha dotted into E, like so. Okay, we get that commutator. Now, this commutator here, let's look at this. That's beta times alpha dotted into pi times beta alpha dotted into E, minus the term swapped. Now, beta anticommutes with alpha. This beta anticommutes with alpha, but it commutes with pi because pi is purely spatial and beta is purely a spin. So I can move this beta to the left of the alpha dotted into pi if I introduce a minus sign because it's an anti-commutator. But that gives me a beta squared on the left-hand side, which is just 1. So this turns into minus alpha dotted into pi. And then we have alpha dotted into e left over. And then this term gives us a plus, the two terms swapped. In other words, I can drop the betas in this commutator if I just change the sign of the commutator. So this thing then turns into, to write it out, it becomes minus 1 over 2m times iq over 2m times the commutator of alpha dotted with pi with alpha dotted with the electric field. All right. Now then, let's do this commutator. Let's write this out as alpha I. Let's see, am I running off the page here? This is alpha I pi j, alpha I pi I times alpha j ej. And commuting spin operators to the left, I get alpha I alpha j, and spatial operators to the right, I get pi I ej. I'm sorry, this is in with a minus sign. I have to swap these two. I just gave the first term. To swap the two, I get minus alpha j ej times alpha I pi I. And so over here, I have to subtract the other term too. So that becomes alpha j alpha I times ej pi I, like so. All right, taking to both terms of the commutator. Now then, let's use our formula for alpha I alpha j. First one's alpha I alpha j, the other one's got the I and the j swapped. So in the first term, we get Kronecker delta ij plus I epsilon ijk times capital sigma k multiplied onto pi I ej. And for the second term, I get same thing here, except I'm going to swap I and j. So it's delta ji plus I epsilon j ik sigma k. And then I have ej pi I. Okay. Now let's take the Kronecker delta terms first. Delta ij, so you get a pi dotted into the electric field here for this first term. For this term, you're going to get e dotted into pi with a minus sign. Pi dot e minus e dotted into pi. It's a kind of a commutator, as you can see. For the other two terms, let's write them out. The first term is going to be this. So we get plus I. Well, the epsilon ijk, of course, this is dotted with 3 vectors here, 1, 2, 3. It gives us a kind of a triple product. The pi and the e don't commute, but the sigma commutes with them because sigma is purely spin. So I can write it this way: is I times the I goes with pi, the j goes with e. So it's a pi crossed with the electric field E dotted into the spin sigma, like so. All right, I hope I did that right. And then for the second term here, we have minus I. And if you look at this, you'll find this is minus I times E crossed with pi dotted into sigma. Okay, now then, let's clean this up a little bit. Let's take the first part here. We can write this as the commutator of pi I with ei. That's to say there's a sum on I here. So it's pi dotted into e minus e dotted into pi. That's what we have up above. But using the standard commutators of momentum with functions of position, this gives us minus I times partial of ei with respect to xi, which is therefore minus I times the divergence of the electric field. That, of course, is related to the charge density. It's 4 pi rho for the charge density. As far as the second two terms are concerned, let's collect the common factor of sigma. Let's write this out. So the result is this whole thing is going to become equal to minus I times del dot E. And then we get plus I, or let me do it this way. Let me take the second term first. Minus I, and then what we have is electric field crossed with pi minus pi crossed with the electric field dotted into sigma. Okay. So this is what we get for the, after some work, for the LSE squared. That's what, if I follow this down, this is equal to LS squared E, like so. We need to multiply by 1/2 in order to get the contribution from the Hamiltonian, as you see right there. And so if we do this, and we also need to multiply, since this is, oh, excuse me, let me make sure I'm doing this right. I'm sorry, this isn't quite right. Let me do it right. This isn't quite right because I started this commutator and traced it all down. This answer that's down here at the bottom is the same as this commutator up above. It needs to be multiplied by all this stuff here, and additionally by a factor of 1/2 if I want to get the term in the Hamiltonian. So to do it right then, 1/2 of 1/2m, 1/2m times IQ/2m times times all of this above, all of this stuff above. That's equal to the 1/2 LS squared E, which is the term in the Hamiltonian. All right. Now, if you work this out, what you find is that the term that involves del dot E turns into the Darwin term in the fine structure corrections. And this term here with the E cross pi minus pi cross E, this is all at fourth order. And so at fourth order, you can replace pi by the momentum P because the correction term is of higher order. So you get E cross P minus P cross E. Perhaps you remember that from the final exam last semester. This is the expression for the spin-orbit interaction when the electric field is not radial. If the electric field is radial, as it would be in a central force problem in an atom, then E is proportional to the radius vector, and you get R cross P, which is of course the orbital angular momentum L. Then these two terms become equal, and you get basically with a factor of 2 L dotted into sigma. That turns into the spin orbit correction L dot S when you take the upper block. In any case, to summarize the results. By the way, in doing this calculation, it's easy to make a mistake of a factor of I or a factor of 2, and I think I've done it right in my lecture, but I found an error, well, at least one error in the notes that I will correct. It is a little difficult not to make a mistake. But in any case, that's what's coming out here. We get all three terms, the relativistic kinetic energy, the Darwin term, and the spin orbit correction are all emerge by carrying out this perturbation expansion. And I've created here a summary page that shows you how it works out for the fine structure. And this is what we get here for the fine structure, is that from the Dirac, and here what I've done is I've taken the expressions that we got that I just evaluated and restored ordinary units in which H bar and C make their appearance again. And so in the so I've actually done two things here. I've taken the block diagonalized Dirac 4x4 matrix Hamiltonian, but since it's block diagonalized, I can just read off the upper two component block. And if I do that, the beta, for example, just turns into the identity and so on down the line. The capital sigma turns into a Pauli sigma. And so I've done that. This gives us, in effect, the upper 2x2 block of the Dirac now decoupled operator. And this is at order 8 to the 4th. And you see here is the relativistic kinetic energy expression. Here is the Darwin term, and here is the spin orbit term. The S here, by the way, is the same thing as sigma dotted, is H bar times sigma over 2 on restoring the H bars. If I now put in E as being the radial electric field, or related to the potential V, which is Q times phi, then you can translate it into these expressions that we had last semester, and they agree exactly. They work out perfectly. All right, so this is, I think, is a nice thing to do at the end of the second semester, because it derives this hand wavy stuff that it derives by a rigorous procedure, the hand wavy stuff we did last semester in terms of generating these relativistic corrections. The relativistic corrections are small, but they're certainly important in many applications. They're important they're big enough. Let's put it that way. They're big enough, and they're smallest of all, of course, for hydrogen. But in higher Z atoms, they become more important, and the dependence goes like Z squared. And so they turn out to be of practical importance in quite a few contexts. So they're not just we're not just picking a gnat's eyebrow here and talking about these things. They're actually of considerable practical importance. And this then is an honest derivation of them. But it's not just an honest derivation. I want you to appreciate where this came from, because in following Dirac's program and constructing his equation, we made the simplest assumptions that could be made following his ideas of a wave equation first order in space and time, so it could be relativistically covariant. We took the simplest representation of the Dirac algebra of matrices. It was necessary to reproduce the solutions of the Klein-Gordon equation and therefore the relativistic energy and momentum relationships. And then finally, we used minimal coupling to introduce the interaction with the electromagnetic field. In fact, we know minimal coupling isn't exactly right, because the G factor of the electron isn't exactly 2, and other particles have G factors that are quite different from 2. But it's close enough to 2 that it shows us that we're capturing a large part of the physics of the electron by means of this procedure. And that physics is so rich that it produces not only the Pauli equation with the correct G factor, but it actually reproduces all of the fine structure terms, including the rather subtle Darwin term, which would be really it's hard to hand wave this one very much. And in addition, in the spin orbit term, remember there's this factor of 1/2 from the Thomas precession, which if you're going to try to rationalize it on the basis of essentially, hand wavy relativistic corrections to a non-relativistic framework, as we did last semester, you have to go through a procedure of composing a sequence of infinitesimal boosts as the electron moves around in its orbit, and then compute the net rotation that comes from the non-commutativity of the boost once you get all the way around, in order to ultimately find that there's a factor of 1/2 correction in the spin precession of the electron in the magnetic field as it sees in its rest frame. I mean, it's really a complicated story. And it all comes out exactly, including the factor of 2 from the Dirac equation. So this is really impressive. And in fact, it's one of the most beautiful demonstrations of non-trivial results from simple beginnings anywhere in physics. And for all those reasons, I think I personally feel it's worthwhile to present this in this course at this time. All right. Now then, that then leaves me with, as I see, I got through this more quickly than I thought I would. That leaves me with 1/2 hour in which to talk about the rest, well, 1/2 hour for the rest of the course. And so it's impossible to do anything substantial in that time. But if I had another week to lecture, I would go on with the notes and hopefully try to finish them. So let me try to do what I can do in the next few minutes to give you at least a bird's eye view and overview of where this would go in the next step. To make a long story short, we're really following a roughly historical sequence of presentation of the Dirac theory of the Dirac equation. You don't have to do that. You can jump right to the modern point of view. But the advantage of doing this is it motivates what is inherent in the modern point of view, which I think otherwise has a lot of things that are hard to understand where they ever came from. So if we put ourselves in the shoes of Dirac or somebody in the period of about 1930 or so, you look at all of this stuff and you say to yourself, this Dirac equation has got a huge amount of stuff in it that must be right. I mean, how could it ever do these things, like create all this perfect agreement with fine structure and not be mostly right? But on the other hand, it has some problems too, and the biggest one is the existence of the negative energy solutions, which, at least in that day anyway, putting yourself in those shoes, there's no interpretation for them. So what I've done in my notes is I've got a rather long chapter on solutions to the Dirac equation and other material too, but let me emphasize just a few points that I want to emphasize or give highlights of some of the material. In the first place, we study at rather some great length free particle solutions of the Dirac equation. You might think free particle solutions would be trivial, and their space-time dependence, in fact, is trivial. It's just, it's just e to the I p dot x minus et over h bar. It's the obvious dependence on on energy and momentum, except the momentum and energy are related by the relativistic relations now, not the non-relativistic ones. But anyway, that's the space-time dependence. But what's more difficult is the spinner part of this. It multiplies out front, and there's quite a bit of machinery involved in free particle spinners, and having to do boosts and so on, and that's one of the things you learn about. There would be no point in me, even if I had an extra lecture, there'd be no point in me going over that material because we'd never have a chance to use it unless we get a little bit further, and you could actually do some calculations with it. But you need the free particle solutions because, number one, they give you a complete set that you can do all kinds of theoretical explorations with. And maybe more importantly, they're used to expand the Dirac field as linear combinations of free particle solutions, which ultimately forms the basis of the second quantization of the field. And then these become, in effect, the normal modes, which become quantized much as the normal modes of the electromagnetic field were quantized when we passed over to a quantum description of the electromagnetic field. So for all those reasons, one needs to go through, if you want to do that, if you want to get into the field theory of the Dirac equation, it's necessary to master the technical details of the free particle solutions. And it's all there in this next set of notes if you want to read it. Let me just tell you a few features that arise, however. I want to talk about the spectrum, the energy spectrum of the free particle Dirac equation. There's first of all an energy of 0 here, and then at some positive energy is mc squared, which is the rest mass of the electron, and down below is minus mc squared. Well, you get a spectrum which starts at a positive energy spectrum. It starts at mc squared and goes out to infinity, like so. The plus mc squared would normally be subtracted off in the non-relativistic theory to eliminate that part of the energy. And so this just corresponds to the usual electrons whose kinetic energy starts with 0 and goes to infinity, except now we have a relativistic description of them. That's what that represents. However, the mathematics of solving the Dirac equation gives rise also to negative energy solutions, which don't make much sense in looking at them. In a number of ways, they're difficult to understand, but mathematically they're there, and their energies are negative, and they start at minus mc squared and they go down to minus infinity, like that. And so the full spectrum of the free particle Dirac operator has an energy gap between minus mc squared and plus mc squared. Also, one of the things you find is that the negative energy solutions of the free particle Dirac equation, in a certain sense, they have not only negative energy, but they also have negative momentum and negative spin. And again, it's hard to interpret what the heck that means, but that's what comes out of the theory on looking at the solutions. So, so there we are. That's what we've got. Now, if you're in the shoes of Dirac and other people around 1930 or something, you might be tempted to say, since we don't see negative energy electrons, we have no idea what that would even mean in the real world, that maybe these solutions down here are all non-physical. You've got a Hilbert space and it's spanned by the positive energy solutions and the negative energy ones. In the mathematical Hilbert space, maybe the one negative energy Hilbert space is just simply non-physical. You know, that's one idea. Okay, well, it turns out that doesn't work for quite a number of reasons. Let me start by giving you one reason why that doesn't work. One reason is that you can not only solve for the free particle, you can also solve other systems, such as notably the hydrogen atom. The solution of the hydrogen atom is rather technical, and even if I had time to lecture on it, I wouldn't, because it's too technical, I think, for an introductory course like this. But there's some, if you're interested in the details, they're in the notes, but you can regard that as kind of for reference for people that really want to get into the technical details. However, there's an overview of this. There's some highlights that are worth knowing about, and let me tell you about them. So first of all, let's talk about the energy spectrum. So here's the energy like this. Well, again, there's we need to mark off the energy mc squared and the energy 0. Let's mark those two off. The Dirac hydrogen atom has an energy spectrum that starts with mc squared, a continuous spectrum, and goes out to plus infinity. Again, the mc squared is just a constant. If you subtract it off to get the non-relativistic version, this corresponds to the positive energy solutions of the hydrogen atom, whose energy starts with 0 and goes out to infinity. These are the unbounded solutions. Somewhat below that are the bound states, of which there's an infinite number. I'll put 2 dots there in the axis to indicate the bound states. And the bottom one is, of course, at minus 13.6 electron volts, relative to the plus mc squared. Well, plus mc squared is equal to 511 kilo electron volts. So these bound states are this is grossly not to scale, this diagram that I wrote. These bound states are down by about 1 part in 10 to the fourth compared to the energy scale mc squared here. It's really rather small, but there are bound states in there slightly below plus mc squared. The Dirac equation, however, like the free particle equation, also has negative energy solutions. And it turns out they start at minus mc squared, the continuous spectrum that goes down to minus infinity, like so. There are no bound states down here at all, just continuum, like that. And so that's the spectrum of the Dirac hydrogen atom. Now then, here's the problem with trying to declare that the negative energy states are non-physical. The problem is that the negative energy states of the hydrogen atom span a different subspace of the Hilbert space than the negative energy states of the free particle. If we were to declare that the free particle negative energy states were non-physical, that the physical Hilbert space was just the positive energy electron states alone, then we'd have a problem, because the positive energy hydrogen atom states cannot be represented as linear combinations of the positive energy electron states. It's necessary to include negative energy electron states as well to get the positive energy hydrogen atom states. And that's because these negative, positive, and negative energy subspaces in these two cases are not the same subspace. In fact, one can see that the negative energy components of the positive energy solutions of the hydrogen atom lie behind the Darwin term in what's called the Zitterbewegung, which you can read about in the notes. There's a long history of that. So in other words, there's no consistent way to define a subspace of the Dirac, call it nominal Dirac Hilbert space, which is to be declared non-physical. That's one problem with this. Let me show you another problem with declaring the negative energy states to be non-physical. Let's recall the Thomson cross-section. The Thomson cross-section is low energy scattering of photons. It's gamma plus electron goes to gamma plus electron, except they scatter, so the final state is different from the initial state. And the d sigma d omega is the classical radius of the electron squared times the dot product of the polarization vectors squared, like this. If you recall, that's Thomson cross-section. You may also recall that when we calculated non-relativistically, there were 3 Feynman diagrams, and they look like this. There was a seagull diagram, and then there were diagrams that had a pair of 3-point vertices that looked like this. And you will also recall that the second order, the 3-point vertex diagrams were of order V over C compared to the seagull diagram, which was dominant. And so the answer came strictly from the seagull diagram. I assume you know all that because it was a homework problem a couple of weeks ago. Now the seagull diagram, as you know, comes from the a squared term in the Schrodinger equation. But the Dirac equation doesn't have an a squared term. The Hamiltonian is equal to C times alpha dotted into pi, which is the same thing as P minus Q over CA. If I put the C's back in, that's what it is, plus Q phi. And you can see that the vector potential here, if we were to replace this by the quantum field for the quantized electromagnetic field, you see the interaction Hamiltonian in the Dirac picture is just equal to, with a minus sign, it's equal to the charge Q times alpha dotted into the vector potential. It's first order in the vector potential, and there is no second order term. So we don't have a seagull diagram using the Dirac equation. So where does the seagull diagram come from? If we do the Dirac equation, what do we get? Well, what happens is the seagull diagram basically opens up into 2 diagrams that again sort of look like the 2 over here, like this, except now the intermediate state is a negative energy state, and these are positive energy states. By the way, some people would prefer to write the negative energy states in a different diagram, but let me not get into that now. This is not important in the limited time we've got. The point is the negative energy states are exactly the ones that produce the seagull diagram in the non-relativistic limit. Basically, this internal line just shrinks to a point, and you end up with 2 terms which turn out to be identical and add up to the seagull diagram. That's what happens. And So in other words, if we were to throw, so in other words, if we were to declare the negative energy states to be non-physical, well, look, these intermediate states came from the Dyson series by inserting a resolution of the identity. And a resolution of the identity is supposed to run over all the states of the system, right? But on the other hand, if you have only some states that are physical and some are non-physical, maybe you ought to restrict it to just the physical states. That would be logical, wouldn't it? If that were the case, and you said that positive energy states were the only physical ones, then you wouldn't have any negative energy intermediate states. And what would happen is that the seagull diagram would disappear. But you'd be throwing out the baby with the bathwater, because that's where the whole answer comes from, at least in the non-relativistic limit. So in other words, even to get the non-relativistic answer, much less the relativistic scattering cross-section for electrons by photons, we know the Thomson cross-section is correct. You can derive it by classical E&M, actually. We have to have the negative energy solutions. They're required, at least in a resolution of the identity. Okay, so those are all arguments for the reality, in some sense, of the negative energy solutions, even though we don't see them, and we wouldn't have even know what we were looking at it, what it means to have something have a negative energy. On the other hand, if they are real, then there's other problems that arise. Here's what they are. Let's go back to our hydrogen atom diagram. This is what was bothering Dirac. There are other problems that arise. This hydrogen atom, which we just solved here, I sort of sketched some aspects of the solution. Was the Dirac equation interacting with an external C number, a field, which was the field from the nucleus. That's really where the solution came from. But the electron is surely interacting also with a quantized electromagnetic field, because you can't switch that off. And so in the real hydrogen atom, the various states are only the ground state is really a stationary state. The higher excited states all emit photons and drop into lower states because of the interaction with the field. And normally we say they end up in the ground state down here because that's the lowest energy state. But if the negative energy states are real, then there ought to be transitions possible, from positive energy states to negative energy ones, either from the upper continuum or maybe from the ground state, ordinary ground state of hydrogen, into negative energy states like this. The coupling with the electromagnetic field will give you matrix elements for such transitions. Well, you might briefly hope that maybe the lifetime is the age of the universe or something, so it never happened. No, wrong. It's worse than that. It's like 10 to the minus 23 seconds that it takes for this to happen. Very short period of time. Oppenheimer did the calculation for this. And so this doesn't work. And so you now have the opposite problem. If you declare that those states are real, then you have to explain why there are no radiated transitions down there. By the way, once you made a transition to one of these negative energy states, why wouldn't you keep on making further transitions, going on down, on down, on down like this, going on down forever, so that your hydrogen atom would, in the ground state, in the normal ground state, would self-destruct, emitting an infinite number of energy in a cascade of photons, something which we obviously don't see. So in 1930, Dirac proposed a solution to this problem. He said, perhaps the reason we don't see transitions to lower energy states, this might happen also for particles that are sort of free. Anyway, let's talk about the free particle case. The prospect is raised that you might have a transition from a positive energy free particle, which would be an ordinary electron, in other words, down into one of these negative energy electron states. The caveat that has to be mentioned in this process is that a process like this cannot take place in free space, because you can't conserve energy and momentum to have an electron make a transition to a lower energy state and emit a single photon. That can't happen. On the other hand, if there's something around to absorb the extra momentum to make up for energy and momentum conservation, then it could happen. And so we need to think about this also for the case of free particles. All right, in any case, in the free particle, such a transition would look something like that. All right, so Dirac said maybe the reason we don't see such transitions is because all of the negative energy states are filled, like that. That's to say, electrons are fermions, and we know that no more than one electron can occupy an individual state. And so if all the negative energy states were filled, then it would not be possible to make such a transition, because the states are already filled by the Pauli exclusion principle. Now, there's an infinite number of negative energy electron states. In fact, even if you restrict yourself to just a finite volume, a little cube or something, there's an infinite number inside a single cube because the energy goes down to minus infinity. That's why there's a huge number down there, arbitrarily large negative energy. And so this is going to take, we have to imagine that if they're filled, that somehow the universe is filled with negative energy electrons, which form an infinite density of electrons, therefore infinite density of charge everywhere in space. This leads to another problem, which is, why don't we see this charge? Why don't we see infinite electric fields? Well, maybe Dirac was reasoning, maybe the answer is because even though there's an infinite number of electrons, they're uniformly distributed. And so by symmetry, there's no direction the electric field could point in, it's balanced out by the electrons in all the other directions. So maybe that's the reason for it, something like that. Of course, you'd also have an infinite density of mass, and that'd give gravitational problems. But in 1930, people didn't worry about gravitational problems very much. All right. So in any case, there's issues with this idea. But if the idea were true, what Dirac realized is it gives predictions of there being new physics. And here's why. Let me draw the diagram again. The new physics is this. Let me just draw the free electron diagram. There's the zero. Here's the mc squared, and here's the minus mc squared. And we'll assume that all the states down here are filled like this, below this line, like this, and above the line are the positive energy electrons, which we know about and see in the real world. Now, Dirac reasoned that all the electrons, including the electrons in this, by the way, is called the Dirac sea here of negative energy electrons, that all the electrons, including the electrons in the Dirac sea, do have an interaction with the electromagnetic field. And therefore, if you have a photon that comes along, it could interact with a negative energy electron. Like there's one, let's say here's one of them there. Photon could come in here like this. And if the photon had enough energy, the energy would have to be more than twice mc squared. If it had enough energy, it could promote this up into a positive energy electron. And so this process would be allowed. If his C hypothesis were correct, this process could happen. Well, what would we see physically? In the first place, we'd see the disappearance of a photon whose energy was greater than twice mc squared. In the second place, we'd see the sudden appearance of an ordinary positive energy electron of the kind that we know and see all over the place. But something else would happen too, is the electron that used to be there in the negative energy C would be gone, creating a so-called hole. Now, as we just argued a minute ago, the only way to understand this infinite sea of negative energy electrons is if the electric field of all the electrons cancel out. But if I remove one of them, then the contribution of that electric field of that one electron to the total electric field has now been removed. And so the total electric field, which used to sum up to zero by symmetry, now has to sum up to zero minus the electric field of the electron we just removed. That is to say, it's going to create the electric field of a positive particle of opposite charge. And one can show that in a certain sense, the whole has not only a positive charge, but it's also got a mass, behaves like a particle with the same mass as an electron. And by the way, as a positive energy. So you're removing an electron with negative energy, negative momentum, negative spin, and it's being replaced by a whole which has positive charge, positive energy, positive momentum, and positive spin. And this begins the basis of what we call hole theory. Now, hole theory predicts something else as well. It says, suppose I have a hole and an electron. Let me draw the diagram again. Here's the zero, and here's the mc squared, and here's the minus mc squared. The negative energy C is filled, except it's got one hole. And the positive, and this is energy axis here. And there's a positive energy electron up there. Now then, previously electrons could not make transitions into the negative energy C because all the states were filled. But now there's one state that's not filled. So it's possible to make the transition. This electron can make this transition into that hole. That transition is allowed now because it doesn't violate the Pauli principle. If it does so, it's going to release energy, which presumably comes out in the form of a photon, like this. And this photon will be released with an energy of more than twice mc squared. What happens if we see this? We see a hole which manifests itself as a positive particle, and an ordinary electron disappear, and a photon appears. Now, once again, this process can't occur in vacuum because of energy and momentum conservation. But if there's something around to take up the extra momentum, it certainly can occur, and it does occur. It's called the electron-positron annihilation. One thing you can do is you can, instead of annihilating to one photon, you can annihilate to two, and you get E plus E minus goes to 2 gamma. This is the usual annihilation process for an electron and a positron. So Dirac's whole hypothesis, you see, leads to the prediction of the existence of antimatter, antiparticles. Before Dirac wrote this paper in 1930, nobody had even any conception there was such a thing as antimatter. As far as I know, the idea never crossed anybody's mind whatsoever. So this came out of the blue. It was purely theoretical. There was no experimental support for it. Dirac realized there was a real problem here, that nobody had ever seen these positive particles. And he thought, well, maybe I can jiggle things so that the proton is this positive particle. But it was quickly pointed out by all kinds of theorists who jumped all over it that this was ridiculous. The proton has the wrong mass by a factor of 2,000 and a lot of other reasons. One theorist who was particularly hot to do this, to destroy Dirac's crazy idea, was Pauli. Pauli was the one who, had hoped against hope to produce the correct relativistic theory of the electron, and Dirac had beaten him to the punch. And he sort of never forgave Dirac. He spent the rest of his life trying to pick at what Dirac did, and if Dirac had ideas that he knew was wrong, he'd write a paper saying why the idea was wrong and so on. He kind of never got over it. But anyway, Pauli was quite critical of this idea that maybe this positive particles were protons, because it didn't make any sense. However, it was only a matter of about a year or so that positrons were discovered experimentally in cosmic ray tracks after Dirac's paper. So Dirac was completely vindicated in his prediction of antimatter, and this is how antimatter came onto the map. Now then, I don't spend any time, even if I had time to lecture on the next couple of notes, I don't spend any time in what's called hole theory, because it's not the modern point of view, and it has in itself, although it does explain things, it has many drawbacks. One of them is that it's not particularly aesthetic. Who wants to think about the universe being filled with electrons? And by the way, why not being filled with positrons? Why bias against electrons? And electrons and positrons. There's a symmetry between electrons and positrons. There's lots of reasons not to like hole theory, and so I wouldn't spend any time on it. But hole theory is vitally important conceptually, because what it showed is that the Dirac equation that we started out with, even starting with what Schrodinger did in trying to write down a relativistic wave equation, we thought we were writing down a wave equation for a single relativistic particle. It seemed easy, didn't it? We had the Schrodinger equation for a single particle. All we want to do is just allow it to write it down for high velocities. It sounds easy. But it turns out that you can't do it. If you try to do it, what you end up with is something which is secretly a mini particle theory. That's what the Dirac theory is doing. It says this is really a mini particle theory. It's not a single particle theory. Well, the right way to handle multi-particle theories is by means of field theory. We saw this in the case of photons. Field theory automatically handles many particles, the possibility of creating and destroying particles. It also handles automatically the symmetry, or in this case of electrons, the antisymmetry of the wave function, depending on whether it's a boson or a fermion. This is all done by means of quantizing the classical field and taking the amplitudes of the classical field variables and reinterpreting them as basically they become creation and annihilation operators for particles of the quantized field. And this can all be done with the Dirac equation, and I've got a set of notes on that if you want to read it. It's an introduction to it. If you want to see a more serious or sophisticated way of doing this, then you should take the field theory course, Physics 232 and 233, where you'll have all this material is just by way of introduction to a course like that. In any case, the multi-particle theory then leads into field theory, and ultimately this is the lesson which came out after some rather painful misconceptions and missteps along the way of this story of relativistic quantum mechanics, starting with Schrodinger. As the ultimate conclusion is that field theory is the way to go, and that everything is really quantum fields interacting with one another. By the way, the Klein-Gordon equation, remember, was abandoned because not only did it have a non-negative, a quote probability density that had negative values, which is definitely bad, but it also had negative energy solutions. Also, the Dirac scheme for the Dirac equation of solving the negative energy solution problem by postulating a negative energy C, that won't work for the Klein-Gordon equation because the Klein-Gordon particles are bosons, and so there is no exclusion principle. But after you've second quantized the Dirac equation, then you realize that the right thing to do is to second quantize the Klein-Gordon equation. And the negative energy solutions of the Klein-Gordon equation, when second quantized, become representations of antiparticles of opposite charge, in case they have charge, of opposite charge, but positive energy, positive momentum, and so on. And so the rehabilitation of the Klein-Gordon equation is to reinterpret it as a field in which the formerly negative energy solutions become, get their amplitudes become creation and annihilation operators for antiparticles. And so quantum field theory emerges from the attempt historically, it emerged from the attempt of developing relativistic wave equations for single particles, which ultimately fails. And that in fact would form, with a semester would be slightly longer, that in fact would form a nice stopping point for, I think, the content of both semesters of this course. Okay, so I did a good job. I ended with about 1 minute before 8 o'clock. So with that quick overview of some of this remaining material. Thank you for your attention for the entire semester. Let me just pause and ask if there's any questions about any of this. All right, no questions. Then if that's the case, then so let's see. So there won't be any final homework. I might put out some little brief note or something tomorrow, but there won't be any homework. I will have office hours tomorrow as usual. I'll be available for questions. You can send me questions by email. I'll decide whether I'll hold office hours next week. I will if I need to. If I do, it'll be at this usual time. So next week, of course, is dead week. And the schedule for the final exam has been published. I mean, I sent you emails, and I think it's on the website. I'll double check and make sure that's all up to date. In case you haven't seen it yet, the final exam is going to be something like a final homework exercise. And you'll have 48 hours to do it, 2 solid days. I want to make it an integer number of days because there are some people who are not in the California time zone. And I want to make it fair to be 2 equal days. That's about it. Again, thank you for your attention for this semester. And one last chance, any questions? All right, then I'm going to close down for tonight.
Thank you,